Okay, let's dive right into this. Welcome to This Explainer. Today, we're tackling what is, let's be honest, notoriously one of the absolute toughest concepts in the Cambridge Additional Mathematics syllabus, applying integration to plane areas. Looking through the 0606 syllabus material, it's super clear we can't just treat this as one single math hurdle. Honestly, it's way more like the Olympic decathlon of exams. It's this massive, multidiscipline event. Think about it. To snag full marks on one of those brutal 8 or 10-mark questions, you've got to flawlessly navigate simultaneous equations just to find your limits, then apply the right calculus rules, carefully sub in your boundaries, figure out what to do with negative areas, and on top of all that, perfectly structure your final presentation. It's a total endurance test, and strategy is literally everything here. I mean, if you drop the algebra early on, flawless calculus later, yeah, it's not going to save the day. So let's break down how to actually conquer this event together.
So here's the golden question, right? What actually separates a B-grade candidate from an A-star candidate when we're talking about integrating plane areas? You might think, oh, it's just natural math talent, or they just never make careless arithmetic mistakes. But when you look at this through the lens of the principal examiners, the folks actually designing these Cambridge papers and writing the mark schemes, a completely different reality emerges. It turns out the difference isn't just about magically getting that final number right. It's entirely about how well you communicate your underlying theoretical architecture. So today, we're pulling back the curtain to explore exactly what these examiners are desperately searching for to guarantee you hit those top-tier grades.
To get you to that A-star standard, here is our roadmap for today. We'll start with the core principles, then unpack the method mark strategy, move into deconstruct, solve, evaluate, and wrap up with the top examiner warnings. All right, let's kick things off with part 1, core principles, the absolute foundation of plane areas.
Evaluating plane areas using integration requires way more than just, memorizing the power rule. We need a systematic analysis and evidence-based reasoning approach. You absolutely cannot just guess your boundaries and start blindly crunching numbers. To really see this in action, let's look at 2 typical students taking on a massive 8-mark question about the area between a quadratic curve and a straight line. First up, we've got Alex. Now, Alex is awesome at raw calculus. He just dives right in, starts integrating the curve equation immediately. He completely overloads the page with raw math facts, but zero analysis. He doesn't actually show the simultaneous equations he used to find the intersection points. And because he didn't establish that causal relationship between the 2 equations, bam, he loses his method marks instantly. Then we have Sam. Sam finds the intersections perfectly, but she rushes the actual integration phase. The question's command word was specifically, show that the area is exactly 12.5, but Sam just skips writing out the substituted upper and lower limits. By missing that core command word requirement, her answer, even though the final number is right, just bleeds marks. We've all felt that exam time crunch, but both of these flawed initial approaches lose points before the complex calculations even really start.
Now, what's really fascinating from the principal examiner reports is this specific note. Candidates referencing cross-topic connections achieve significantly higher marks. Integrating plane areas, that is the ultimate cross-topic challenge. Think about it. We're blending coordinate geometry to find the equation of a line, simultaneous equations to find intersection limits, maybe some trigonometry if the bounding curve happens to be a sine function, and then, finally, calculus. Mastering the fundamentals means recognizing that we are never just doing one single type of math here. When you explicitly show you're working for the coordinate geometry step before smoothly transitioning into the calculus step, examiners absolutely love it. They heavily reward that analytical depth.
Which perfectly brings us to Section 2, the method mark strategy. This is all about prioritizing the process over the final numbers. Okay, this strategy requires a massive mindset shift. The academic benchmarks for additional mathematics demand logical, structured reasoning. If you look at Cambridge mark schemes, you'll constantly see marks labeled M1 or DM1. Those are method marks. They're awarded purely for demonstrating a logical, structured, analytical process. So if you set up the definite integral correctly, like you've got the right upper and lower limits and the correct expression for the upper curve minus the lower curve, you earn the method mark. And let's be super honest here, there is literally nothing more painfully relatable than doing 10 minutes of flawless, brilliant calculus only to accidentally write that 2 plus 2 equals 5 at the very end, right? We've all done it. But the beautiful thing about this method framework is that it shifts your anxiety away from that final answer and refocuses your energy on proving the methodology. The examiner just wants to see your brain on the paper.
So how do we actually guarantee we get these method marks? Well, we take a classic analytical framework, PEEL, and adapt it specifically for mathematics. Top-tier students use this flow to rhythmically structure their answers. Step 1 is the point. Just identify your objective. Simply state something like, area equals the integral of the upper curve minus the lower line. Step 2 is evidence. Extract your data. Explicitly write down the limits you found using simultaneous equations. Step 3 is explanation. This is your clear, line-by-line working out of the antiderivatives and boundary substitutions. Seriously, do not skip steps here. And finally, step 4 is the link. Contextualize your result. If you calculated 2 separate areas, explicitly state total area equals area 1 plus area 2, linking your math back to the specific shaded region on the page.
Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, let's jump into section 3, deconstruct, solve, evaluate. This is your master workflow.
When you're staring down a terrifyingly complex shaded region bounded by 2 intersecting curves and an axis, there's a standardized sequence you can rely on to keep your panic at absolute zero. And this breaks it down brilliantly. Step 1. Identify key elements. What actually are the equations? Which axis is the area bounded by? Step 2. Apply relevant principles. Like, do we need to integrate with respect to x? Or, actually, is it going to be way easier to integrate with respect to y? Step 3. Execute the analysis. This is your clear, methodical working. Step 4. Verify results. Check for reasonableness here. I mean, if you're finding a physical area and your result comes out negative, you probably need to double-check if you subtracted the top curve from the bottom curve the right way around. Finally, Step 5. Present it in the appropriate format, making sure you use proper terminology and write units squared.
Let's try a quick mental data scan challenge together right now. Just imagine a 60-second timer is ticking down. You're presented with complex data, multiple intersecting points, a quadratic curve bounding from the top, a linear equation slicing right through the middle. The skill you need here is extracting the core mathematical trend and doing it fast. We need to be able to visually recognize that, okay, from x equals -2 to x equals 0, the area is just the integral of the curve. But from x equals 0 to x equals 3, the area is the integral of the upper curve minus the lower line. Seeing that split? That is the entire secret to unlocking this puzzle.
So, let's see how candidates actually write out their solutions once they've scanned that data. Can you spot the flaw in the generic approach here? The flawed answer just slaps down a single integral sign from -2 to 3, blindly shoving both equations in without stating any assumptions. They totally fail to recognize that the area splits right at the y-axis. The mastered approach, on the other hand, uses context-specific reasoning. They clearly define area 1 and area 2 as separate things. They use crystal-clear notation, carefully placing brackets around their polynomials before subtracting them, which totally saves them from those classic, super frustrating negative sign distribution errors. The examiner commentary on this exact scenario explicitly says that an evaluated, distinct, and specific methodology secures full marks, while generically blending equations is heavily penalized.
Let's do a speed writing challenge to really cement this active learning. Visualize a 30-second timer counting down. How do we mentally construct a perfect PEL application for finding the area between the curve y equals x squared and the line y equals 4? Okay, point. Find the points of intersection to establish limits. Evidence. Setting x squared equal to 4 gives limits of x equals 2 and x equals -2. Explanation. I'll integrate the upper function, which is the line y equals 4, minus the lower function, the curve x squared, between -2 and 2. Link. I will evaluate the definite integral to find the exact enclosed area. If we can instantly formulate that structure in our heads, we are thinking exactly like A-star candidates.
Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, let's move into our final act, Section 4, Top Examiner Warnings, and exactly how to avoid the major pitfalls.
After analyzing years and years of exam data, there are exactly 3 critical mistakes that Cambridge examiners consistently highlight when it comes to integrating plane areas. Memorizing these 3 pitfalls is honestly your ultimate defense mechanism on exam day.
Pitfall number 1, confusing cause and effect. Examiners report that students frequently misinterpret the relationship between boundaries and curves. Let me give you an example. A student might calculate the x-intercepts, the roots of the equation, and then blindly use those as the limits of integration. They completely ignore the fact that the actual shaded region in the diagram is bounded by the y-axis and some totally different intersecting line. They confuse the cause, which is finding roots, with the effect, which is defining the correct boundary for the specific area requested.
You have got to always verify your algebraic limits against the actual visual geometry of the problem.
Pitfall number 2 is deeply frustrating to see. Forgetting format and presentation. Mathematics is a language, guys, and its presentation follows really strict conventions. Examiners continually flag students who just drop the dx or dy notation at the end of their integrals, or they remove the integration symbol before they actually perform the calculus, or they fail to use square brackets to properly denote the evaluation of limits. These are not just stylistic choices, they are mandatory mathematical conventions. If your notation is sloppy, the examiner literally cannot award the method marks because your logical structure is officially compromised.
And finally, pitfall number 3, providing generic answers. So, the crucial point here is that this classic mistake happens when candidates fail to link their analytical points back to the specific scenario they were given. If a question asks you for the area of a specific weird, triangular-like shape bounded by 2 curves in the x-axis, and your final statement is just some random number floating there with zero context, the job isn't finished. We have to provide a specific conclusion that addresses the exact parameters of the question. You want to clearly state something like, therefore, the total evaluated plane area bounded by the curve in the line is, and then provide your answer.
To completely bypass those pitfalls, we've distilled everything into the Math Success Blueprint. Rule 1. Command word decoding. If the exam explicitly says, show that, we must show every single substitution step. If it says evaluate, we absolutely need a final numerical answer. Rule 2. PEL Framework Application. Always rhythmically structure the process. Point, evidence, explanation, link, to practically guarantee those vital method marks. And Rule 3, the time management matrix. In a standard Cambridge exam, you got roughly 1.5 minutes per mark. So, for an 8-mark plane area question, that gives you 12 minutes. Spend the first 2 minutes deconstructing the graph and finding your limits. Spend 6 minutes executing the heavy integration in algebra, and use your final 4 minutes verifying your result and ensuring your presentation is absolutely flawless.
Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. The knowledge alone isn't enough. Execution is everything. Rigorously practicing past paper questions under timed conditions using this exact blueprint is the ultimate key to translating this theory into undeniable exam success.
Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.
I want to leave you with this final, slightly provocative thought as we gear up to tackle the next set of past papers. When you finish your next 8-mark question on plane areas, take a really hard look at the page. Will your next integration answer just show a single, lonely number floating at the bottom, totally vulnerable to the slightest arithmetic slip? Or will the ink on that page prove your complete analytical mastery, securing every single method mark along the way? The choice, and honestly, the top grade, is entirely in your hands. Keep practicing, stay analytical, and I'll see you in the next explainer.